Hi, everybody. Welcome to Math with ACE. We are going to be focusing on statistics. We have been performing inference, and now we're going to be actually calculating or performing inference for two groups rather than a single group. We have been dealing with proportions and means, and in our previous video, we talked about how you would go about checking conditions and performing calculations, and now we're actually going to put that into practice. And we're going to start out by dealing with means. Now, if you were presented with a question on an assessment or in class and you weren't sure what to do, you really should be asking yourself three questions. The first question is this question asking me to estimate a parameter, which would be a confidence interval, or is this question asking me to test a claim? And if I'm being asked to test a claim at a certain level of significance, that means I need hypothesis testing. So intervals is estimating a parameter, testing a claim is hypothesis testing. So this question asks us to test a claim. We haven't even read it yet, but we also need to ask ourselves, so once we've determined either interval or test, we need to determine, are we talking about proportions or means? And so for proportions, you're given a certain success out of a group or you're told a percentage, whereas means is about the average number, and you're typically also given the standard deviation or you're given a set of data, because proportions are categorical and means are numerical when we're talking about the different types of data. And then once you've established which set you're in, then you're looking at, do I have one sample? Do I have two? And if you're given one set of data, you have one sample. And if you're given two sets of data, you have two. So this question says the average amount of time boys and girls, so average right there, the average amount of time boys and girls also, that's two different groups, age 7 to 11, spend playing sports each day is believed to be the same. A study is done and data were randomly collected, resulting in the data in the table below. Each population has a normal distribution. Well, that's nice. We have our sample size. We have our average number of hours played during sports. We have our sample standard deviation. And it says, is there a difference in the mean amount of time boys and girls age 7 to 11 play sports each day? Test at the 5% level of significance. So we have a lot of information here to unpack. We are given standard deviation. We're given average. This question is about means. And we're given boys and girls, which means that we have two samples. And we are asked to test a claim, which means that this is a hypothesis test. And so because of that, when we go through a four-step process of state, plan, do, conclude, we're stating hypotheses. We're drawing conclusions about rejecting or failing to reject, and so on. So the first thing that we want to do is we want to set up our hypotheses. So actually, I like to say we want to perform a test. And then I write my hypotheses. The question says, is there a difference? It does not say less than, it does not say greater than, it doesn't say least, greatest, any of those. It says difference. And difference to me is not equal to, which means we always start with our equality and our alternative is going to be a not equal to, which means this is two-tailed. So we can either reject high or low depending on the situation. We have means, that means our parameter is mu. And because we have two, we need to denote mu1 versus mu2 here. You could also do mu b, mu g, those types of things. I think that doing mu g and b is a little bit actually more straightforward because you get to see if your girl or boy is first. So let's actually do that. Let's go to, let's say, g and b here. And we need to identify what it is that we're talking about. What does mu g and mu b mean? And so we need to say where mu g is the average number of hours girls age 7 to 11 spend playing sport each day. Defining one is not enough. I need to define both. So I need to say, and mu B is, and then I go on again, is the average number of hours playing sports per day of boys. Okay, and then I also need to establish my level of significance, and we're going to use alpha equals 0.05 level of significance. You can say 5% if you want, but I like to do it as a decimal. So we've identified our parameters in context, we've given our level of significance, and we've established our hypotheses. Remember that you could have said mu G minus mu B equals 0, and mu G minus mu B is not equal to 0. Those are also acceptable methods to write. It's acceptable notation. Now we want to plan, which means we need to check our conditions. And our conditions that we're checking are random, independent, and large count / normal. So let's look at random. A study is done and data were randomly collected. So the data for boys and girls were randomly collected. Notice I said both, and I have boys and girls written. That plural tells me that I'm talking about two groups, not just one. It's important that you talk about two groups here. Independent. Our sample size from above, you might not have written it down, but there were 9 girls and 16 boys that were playing in the situation. So N of G was 9 and N of B was 16. There were 9 girls and 16 boys. And so what that means is I need to multiply each of those by 10 to make sure that we have at least that many people in the population. So 9 for girls, 9 times 10 is 90. And for boys, 16 times 10 is 160. So we need to assume that there's at least 90 girls aged 7 to 11 that are playing sports and at least 160 boys. And I think that's a safe assumption. We're not told that this is like a super small town where there's only, 20 kids, or we're just assuming that we're in a town where there's more than this, and they did a random sample. What about normal or / large counts? This is for means. And remember, for means, there's 3 different ways that you can check your conditions. The populations are stated to be normal, the sample sizes are at least 30, or the graphs show no strong skewness or outliers. Let's work it in reverse. We don't have data. We only have summary statistics. And so we have no graphs to be able to see for these small groups whether there's outliers or skewness. So I can't check the last way. And our sample sizes are not at least 30, which means they have to be given to be normal, and they are. So let's say large counts / normal. The populations were given to be normal. That's nice and easy. Okay, let me scroll down a little bit. So now our conditions are met. We're safe to proceed. So what I need to do now is I need to start calculating. And what we didn't talk about in the last video is degrees of freedom. The actual calculation of degrees of freedom has a very gnarly formula that involves lots of calculations, and we're just going to let our calculator calculate degrees of freedom. You could also do a conservative degrees of freedom to do the sample sizes together, which help us calculate what our degrees of freedom are going to be for when you have more than one sample. There's a few different things that you can do for degrees of freedom. Just a little sidebar here. You can let the computer or calculator calculate it for you. And you'll get something that is not a whole number. You could use the approach of adding the two sample sizes and subtracting 2. So you could do n1 plus n2 minus 2. Or you can do the smaller of n1 minus 1 or n2 minus 1. So I'm going to show you what happens when we do each of these so that you can get an idea of your p-value. When we are calculating our test statistic, we have to take the difference in the sample means minus the hypothesized value differences, and then we are dividing that, I'm going to scroll down just a little bit, by the square root of the first sample standard deviation squared over the first sample size plus the second standard deviation of the sample over the second sample size, and we're squaring them. Well, we were using B and G, and notice in our hypotheses we did G first. So the way that this would look is instead of 1 and 2, we would have girl. So all of these would be girl values, and then boy. All of these would be boy values. Okay. The girl average was 2. So X bar G was 2, and S of G was 0.866. X bar B was 3.2, and S of B was 1. That was from the table above. Okay, so we have that information, and then we can go ahead and plug that into our formula. Okay, I had to wait for our screen to catch up. So now we can plug in those formulas, or those values into the formula. The average of girls was 2. The average of boys was 3 minus 2. And then in the hypothesis, we were assuming that the 2 were equal, and so there is no difference, which is 0. We're then going to square root the standard deviation of girls was 0.866 squared over the sample size, which was 9. Adding that to the standard deviation of boys was 1 squared over the sample size of 16. So that leaves us with a numerator of negative 1.1.2, and then in the denominator we have 0.382, which gives us a t-value of negative 3.141 for doing that by hand. So now I'm going to show you how to get the p-value in Statlet. I'm going to show you with all 3 measures of degrees of freedom. So we could have a p-value when our degrees of freedom are from technology. We could have a p-value if we're using the degrees of freedom that are conservative, which is the smaller of n1 minus 1 or n2 minus 1. So the sample size for the girls minus 1 is 8. The sample size for the boys minus 1 is 15. So 8 is the smaller. So I could use degrees of freedom with 8. I could also, I'm going to move the screen down just a little bit. N1 plus N2 minus 2 is 23. So I could do a p-value with my degrees of freedom of 23. Using technology is always going to be the best, but using the degrees of freedom that is conservative is going to give us, let's see how they play out. So let's go into the t-distribution, and we're going to calculate the area. Our degrees of freedom, let's start with 8. And we're going to say outside a region where we have our negative 3.141 and 3.141. Here, we have them duplicated on either side, which is an area of 1.38%. So I'm going to write that as 0.0138. You could also say to the left of negative 3.141, but remember you have to double that because this is a two-tailed test. So you find to the left, but then you double. That's the tricky part of doing it with just t-distributions and knowing what you have to do based on your alternative claim. What if we did degrees of freedom of 23? We get 0.23%, which we would double, or we go outside negative 3.141. And 3.141, which is 0.46. So that is 0.0046, which is smaller. So the area, when you use the higher degrees of freedom, is even smaller. What if we did it with our calculation where we went into perform inference? One quantitative variable, multiple groups. This is hours playing sports. We have to do the mean and the standard deviation. We do not have raw data. Our girls had a mean of 2, a standard deviation of 0.866, and 9 in their group. Our boys had a mean of 3.2, the standard deviation was 1, and the sample size was 16. We begin analysis, and then we need to tell it we want to test. We do not want conservative degrees of freedom, but our alternative needs to be not equal to. So when we perform inference, we get roughly the same t-value. We're off by the 1,000th, but our p-value is 0.005. I think if I did, let's say I adjust my rounding to say 4 digits of precision here. And then I am done. I go back here, 0.0054. So our degrees of freedom of 23 was 0.0046. If you notice, the smallest degrees of freedom gave us the highest probability. Any of these in comparison to our alpha equals 0.05 are going to be a rejection. So let's conclude. Since our p-value of let's use the actual one from the calculations not using conservatives. So since our p-value of 0.005 is less than our alpha equals 0.05 level of significance, we reject the null. And when we reject, what that means is we have evidence for the claim. We have evidence to support the claim that there is a difference. Is that enough? No. A difference in what? A difference in the mean amount of time boys and girls aged 7 to 11 spend playing sports each day. The conclusion, the statement, and the checking of the conditions is roughly the same. The biggest thing to consider is how you're going to do your degrees of freedom. So if the instructions don't dictate how you do your degrees of freedom, it would say maybe use the conservative or use N1 plus N2 minus 2. Use technology. Let technology be the one, run it and perform the inference that way so that you get the most accurate value possible. That is my recommendation to you. Thanks for watching. Hopefully that this was helpful.